Exercise 2.9. Here we want to implement orthogonal vector decomposition. So we start with two random numbers vectors, vector t and vector r. And basically we want to reproduce figure 2.8. So let me just show you that figure. Okay, so here I have two vectors drawn at random from sets of two numbers, because this is all in 2 dimensions. We can do the visualization. Because visualizing things in 6 dimensions is not so easy. So we have a vector t, I call this t for target, and vector r is this gray line here, and r is for reference. So the idea is to decompose this vector t into two other vectors such that the sum of those two vectors is t. And you can visualize that if you think of this intersection here. These two vectors would sum together and produce this vector t here. So that's one condition. Another condition is that these two vectors should be orthogonal to each other. So we're going to need to confirm that empirically in the code by computing the dot product between these two vectors. And we expect that dot product to be 0. And the third condition is that this vector here, which is called t parallel, this is parallel to vector r, and this is perpendicular to vector r. And that's why this is called t perpendicular, and this is called t parallel. The key insight to solving this problem is to see the link to orthogonal projection that I discussed in the chapter, and that we also worked on in the previous exercise. So if you take this vector t and project it onto r, that gives you this point here, but then you can define this point, which in the previous exercise I call this beta a. So we call them different names. We give them different variable names, but it's all the same concepts. So we orthogonally project vector t onto vector r, and this gives us this parallel component of t. And then we just can do vector subtraction. So we just subtract these two vectors, and that gives us the orthogonal component, or the perpendicular component. Okay, so now let's switch to Python. I'll show you how I implemented this in code. Here is another example of where we do not need to worry about orientations in vectors. We don't need these vectors to be row vectors or column vectors. In fact, you could even write all this stuff out using lists, the Python data type list, instead of NumPy arrays, if you want to do. But so I have them as NumPy arrays with randomly generated numbers, 2 numbers for t, 2 numbers for r. So that gives us our 2D vectors that we are going to work with. Here's the decomposition. This, of course, you will recognize from the previous exercise and also from the book. So we have the dot product of t with r divided by the dot product of r with itself. So different variable names compared to the previous exercise, but same concept. So this gives us the scalar. And now to get the vector t parallel, we need to scalar multiply vector r. And then to get t perpendicular, we literally just subtract them. So we start from t and we subtract off the parallel component, and what's left, the residual, is the perpendicular component. Okay, so then I print out this, although this is not going to be super interpretable. We want to see that vector t equals t parallel plus t perpendicular. So the decomposition should be perfect. These two should sum to this. That's not going to be a big surprise based on how I define this. But we also want to confirm the orthogonality, and this result should be 0. Of course, it should be 0 in practice on computers. It might be non-zero, but very, very small. Okay, and then here I just draw everything out. So here we go. So here is vector t. Here is vector t parallel plus t perpendicular, which sum to t. And here we see the dot product between the parallel and the perpendicular components, and you see that that is essentially 0. And here is the graph of all of this. And it's always handy to look at these graphs. Now, we cannot prove, with all these empirical demonstrations, these are demonstrations designed both to help improve your linear algebra coding skills and also to help you build intuition. But these examples don't actually prove anything. You need to work through the the math to get the proofs. These are just empirical demonstrations. Okay, but that said, it is useful to look at these graphs and eyeball things to make sure that they make sense. So this line, so t parallel and t perpendicular, should be orthogonal to each other, which means they should meet at a right angle, and that certainly looks to be the case here. And then, yeah, they should sum to this vector here, t, which, again, visually, that certainly seems plausible. Also interesting to see that the angle between r and t is obtuse. So in fact, this projection goes negative. We get onto negative r over here.